Alright, so I want to start off by just doing a quick definition of energy, and we're going to keep it real simple. Energy is the ability of things to change themselves or cause change in other things. Alright, so take a moment and go ahead and write that definition down. And I want to talk now about how we measure energy.
So we measure energy in a unit called the joule. And to give you an idea of what a joule is how much energy it takes to move an object with a force, I'm using a little scale here, a force of 1 Newton, 1 meter. So if you can move an object using 1 Newton of force over a distance of 1 meter, that is a joule of energy. We also can refer to a joule as a Newton meter, just because it's fun to say. I love saying Newton meter, but a Newton meter, 1 Newton meter is the same as 1 joule. Now this right here, a 100 watt light bulb, has 100 joules of energy every 1 second. Every second it's burning, it expends 100 joules of energy.
So let's take a look at some examples of energy. And we can start off by saying, there's different types of energy, ways of producing it, whether you're burning wood, burning coal to make electricity, or solar, wind power to make electrical energy. There's chemical energy you get from your foods. All different kinds of examples. I want to go through one example here. So I think this is a neat example. This is an evaporation pond. And what they're doing here is they're evaporating ocean water so that they have salt left over, and they can use that salt for different manufacturing purposes. It's not the kind of salt that we sprinkle on our food usually. So the whole premise here is that they dye the water with a blue dye called triphenylmethane because darker colors absorb more heat from the sun. So it's absorbing more energy. Alright? The blue is used instead of black because black dyes are harder to remove when they're all finished up. The blue dye is very inexpensive to remove, so that's why they use that. And so as it absorbs that heat energy, it drives the evaporation of the water, leaving nothing but the salt left over. Now here's where it gets even more interesting. Since this isn't salt that we use on our food, they tend to use salt from evaporation ponds to make bleach, chlorine, or other chemicals like sodium hydroxide, which can be used in soap making and a number of other processes. And the way they do that is they'll take the salt and they'll introduce yet another type of energy, electrical energy, and the electricity will break the salt compounds apart. And salt is made up of sodium and chlorine. It'll break those apart so you'll have pure sodium and pure chlorine, and you can use those to make those other products that I was talking about.
Alright, so the next example I want to use is a pendulum. I have a bowling ball pendulum here, and we can look at kinetic energy and potential energy in more detail. So we'll consider this at a 0 height when it's not moving, and as I raise this up, I'm gaining height with the bob of my pendulum. That would be the bowling ball. So as I bring this up and I gain height, I gain potential energy. The higher I go, I might be out of the screen right now, but the higher I go, the more potential energy this bowling ball has. The lower I go, if I go all the way down, it has no potential energy. It has no potential to move here. But if I bring it up to here, it now has potential. And all I have to do is let go of it, and all that potential energy starts becoming kinetic energy. Now kinetic energy, when I come up here and I hold the ball there, and it's not moving, there is no kinetic energy. Kinetic energy has to be moving. So as I let go of it, the spot where there's going to be the greatest kinetic energy will be right here, because it's going the fastest, before it starts to go back uphill. So I want to look at this mathematically with some more detail. Let's take a look.
Alright, so we're back to the drawing board here. And what we were looking at with that swinging pendulum was potential energy due to gravity. Gravity bringing that down. We call that potential, or gravitational potential energy. And for potential energy, I'm going to use this to represent it, E for energy, with a little subscript of P for potential. And our formula for gravitational potential energy is the mass of the object times the gravitational acceleration, which we know on Earth is 9.8, times the height the object is off the ground. So if this is my pendulum right here hanging straight down, let's say that that bowling ball has a mass of like 5 kilograms. And gravity was 9.8. But just for the sake of keeping our math simple, let's round that up to 10 meters per second squared. But you guys know it's really 9.8 meters per second squared to be a little bit more precise. And it's sitting right here at the bottom. So the height, remember how I said the height there is 0? That'll be 0 meters. So we can do this. Mass times gravity times height. Multiply those all together. There's a 0 in there, so we know the potential energy when it's just sitting there is going to be 0 joules. But if I bring the pendulum up to a certain height, let's say that my height here is 2 meters. Well, now I can do 5 times 10 times 2, which would give me a potential energy of 5 times 10 is 50, times 2, 100 joules of potential energy. So the more I gain in height, the more potential energy. Or the more I gain the mass. If I wanted to make a heavier bowling ball there, that can increase the potential energy. So that's how we calculate potential energy. Alright, so let's do another example of, so we have a pendulum again, and we're going to pull the pendulum back to this location. Alright, and so we're going to be calculating, in this case, instead of potential energy, we're going to let go of the pendulum, and we're going to calculate the kinetic energy, which we could represent with a KE, or E for energy with a little subscript K. The formula is half the mass times the velocity squared. Since kinetic energy has to do with motion, we need to take into consideration its velocity, how fast it is moving. So let me give you a few numbers that we can work out. Let's say we have it up here at a certain height, so it has potential energy, but it's not moving, so its velocity is 0, so it has no kinetic energy. And then we let it go, and it comes racing down to here, and this is where it's going fastest, right here, before it starts going back uphill. And let's say that the mass, we'll give a different mass here than our last example. Let's say the mass is 10 grams, or 10 kilograms, sorry. And the velocity is 5 meters per second. So if we plug in our formula, here's what we're going to get. We'll have the kinetic energy is equal to half the mass, which is 10 kilograms, times the velocity squared. Right? I like to treat this as two different pieces, and it helps me to follow PEMDAS, the order of operations. So I know with PEMDAS I need to do parentheses and exponents first. So I like to treat it like it's two different pieces here. I do this half first. That's square 5. That's 25. And then I can do this where I can multiply half times 10. That's going to give me half of 10 is 5. And then I can just do the last of my order of operations, 5 times 25, which is 125 joules of energy, of kinetic energy. That's how you do kinetic energy.